previous presentation, we talked about electrostatics or charges in place. Now let's talk about moving charges or electric current. So think about when we talked about heat last week or the week before, we learned that heat always flows from a hot object to a cold one. And think about that. When does the flow of heat stop? And the flow of heat usually stops when both objects are the same temperature, so there's no difference in the temperature of the two objects, so the heat doesn't flow anymore. Our electrical charges are the same way. They flow from an area of high charge to an area of low charge. And once those charges are equal, then there's no flow anymore. There's no flow of charge if they're equal. There has to be a difference in potential. There has to be a difference in the level of charge in the two objects. We can think about it when we look at, say, water pressure and things like that. So when the ends of an electrical conductor are at different electrical potentials, when there's a potential difference, the charge flows from one end to the other. And we can look at it like here in our water. If we have a high pressure tank and it's connected to a low pressure tank, well, the water pressure is going to flow from the higher pressure to the lower pressure. And again, when is the water going to stop flowing? Well, when the pressure in the two tanks is equal. Same thing with our charges. The charge is not going to stop flowing when there's no potential difference, when the charges are equal. Now, if we want a charge to keep moving in a conductor, we have to maintain that difference in potential while the charge flows from one end to the other. And again, just like if we go to our water in our tanks, if we wanted the water to flow continuously from the high pressure tank to the low pressure, well, then we'd have to have some type of pump to keep the water moving so that the pressures never became equalized. And when we say potential difference, if you remember from our previous presentation, that potential difference can also be called voltage. And just as the flow of water is a current in a river or stream or something like that, the flow of electric charge is called electric current. And when we have electric current, we're talking about the flow of charged particles. And most of the time, these particles are going to be electrons. As we're looking at this electric flow or current, we measure it in amps or amperes. Most people just say amps. And an ampere is 1 coulomb of charge that passes a certain point per second. And in a wire carrying 1 ampere of current, 1 coulomb passes every point of the wire every second. And then if it was carrying 2 amperes of current, it would be 2 coulombs passing each point of the wire every second. And it's a lot of electrons. One coulomb, again, if you remember, is 6.25 times 10 to the 18th power. And again, to keep these charges flowing, something has to push them. Something has to create that difference in potential. And we can create that difference in potential a couple ways. By generators, we can separate the charges by induction and keep them flowing that way. And we can also use batteries to separate the charge by chemical reactions, and so again keep that charge flowing from one end to the other. Whenever we have a current going through a material, we'll encounter resistance, and resistance is a tendency of the substance to slow that movement of electrons. And this can depend on the type of material. Again, good conductors usually don't have a lot of resistance. Good insulators have a lot of resistance. If we have a substance and we lengthen that substance, well, then that's going to increase resistance too. Longer wires have more resistance than shorter wires. The diameter of the conductor plays a big part too. The larger the diameter, the less the resistance of that object. And also temperature. As we learned about superconductors in the previous presentation, the colder something is, the less resistance. And we measure our resistance in ohms, which is that little omega sign there. The ohm is named for a scientist named George Ohm, and he studied electricity and he created Ohm's law, which states the relationship between voltage, current, and resistance. And this law states that in a circuit, the current will vary in direct proportional to the potential difference or the voltage, and inversely with the resistance. So the more voltage, the more current, but the more resistance, the less current. And we can state this as I equals V divided by R. And that just means our current is going to equal our voltage divided by our resistance. We can also rearrange this equation. Say if we know different variables, we can rearrange the equation to make it easier for us to do the math. We can arrange it as resistance equals voltage divided by current, or the voltage is the current times the resistance. And as long as we know any two of these variables going on with our circuit, we can figure out the other one. And again, increased resistance is going to decrease our voltage and it's going to decrease our current. So the more resistance in a circuit, the less voltage and current. If we decrease the resistance, well, now we're going to increase the voltage and the current. We can also make, when we're constructing electrical circuits, we can construct little devices that regulate the current inside that device. And we can call these devices resistors. And you can see there's some examples of some resistors that might be placed in electrical circuits in the picture. If we're drawing an electrical circuit, the symbol for resistance in the circuit is that little zigzag line that you see there. So now that we know a little bit about current and amps and resistance, we can talk about electrical shock. So electrical shock is the damage to a person that's a result of the current passing through their body. And to get shocked, there has to be a difference in electrical potential between one part of your body and another. And any current going through your body is going to pass along a path of least resistance connecting those 2 points. So if you touch an electrical wire with your hand and your foot is touching the ground, then the path of least resistance is going to be from your hand through your body down through your foot. And you might have seen, say, birds perching on high voltage wires, and you might be wondering, well, why isn't he getting barbecued when he's touching that high tension wire? Because some of those wires can have up to 100,000 volts going through them near power plants. And the difference is, if he's on the wire, there's no difference in potential between his left foot and his right foot. So there's no basically current flowing through his body because there's no difference in potential. There's no way for the current to go through his body because the potential is the same. So the current just goes along the wire, minding its own business. But now let's say this bird happened to grab another wire with one foot. And if that wire had a different potential, well, then now the current could go through his body and down out through the other foot, and he could get shocked. And sometimes this happens. For instance, sometimes squirrels like to make nests in electrical transformers, and that's okay until they have maybe one foot on one wire and that has some high voltage going through it. And then he touches, say, a metal object or another wire with his other foot, and then we have barbecued squirrel, and our transformer goes out, and our lights are out till they can fix it. Now, the human body has a resistance of about 100 ohms if you're soaking wet, to about 500,000 ohms if you're dry. So, if you're dry, you have a lot of resistance. If you're wet, because the minerals in the water can help conduct the current, then your resistance is much less. And so how would that difference affect what you would feel if you happened to grab a wire and a current went through you? Well, the increased resistance reduces the pressure pushing the current through your body. So the potential between you and the ground is going to be quite small. Say if you had a 120-volt household appliance that somehow malfunctioned and you touched it and you got shocked, it would hurt. You would feel the shock, but you'd probably be okay if you were just standing on the floor or whatever. But not, let's say you are soaking wet and you are standing in a wet bathtub. Oh, well, now the resistance between you and the bathtub you're standing on is very small. And if resistance is small, remember what happens to the current. Well, let's work this out. Let's say, okay, our current is going to equal 120 volts, which is the household voltage, divided by our very low resistance, 100 ohms, and we get a current of 1.2 amps. And what does this 1.2 amps mean to us in terms of being shocked? Well, if you have 0.001 amps go through your body, you can feel it. 0.005 amps is painful, hurts. Zero point zero 0.01 amp causes involuntary muscle spasms. At 0.015 amps, you have no control over your muscles. And at 0.07, that can be fatal if longer than a second. And of course, that 0.07 is much less than the 1.2 amps we saw we would receive in the previous slide. So don't touch electrical stuff when you're wet. We can have two ways that current can flow through a circuit. The first way we're going to talk about is direct current. And this is a circuit in which the current flows in just one direction. And this is typically seen in things like batteries. In batteries, the electrons come out of one pole, go through the circuit, and then, as we see in this picture, the electrons can go through the circuit, light up the light bulb, and then return back to the battery to complete the circuit. And our batteries have that positive and negative terminal, so this is the push that causes the electrons to flow. And they can be different types of potential in our batteries. We can have, say, 12-volt car batteries, which is a pretty high potential for a battery, all the way down to, say, the 1.5 AA batteries that you might use in a small flashlight. There's only 1.5 volts of potential difference between the poles. We can also have alternating current, and in this case, the electrons move back and forth in the circuit. They don't just move in one direction, they kind of vibrate back and forth in place. And this polarity in that voltage, the moving back and forth, starts at the generator. And when we talk about magnetism next week, we'll find out why that is. We can measure the rate of vibration back and forth, the directional change of our electrons, and that's measured in hertz, like our sound waves are measured in hertz. And the current that we have in our houses here in the United States is 60 hertz. So that means the electrons are going back and forth in the wires in your house 60 times per second. If you move to another country, other countries might have their electricity coming into residential areas at a different frequency. For instance, in Europe, most of Europe uses 50 hertz, which is why if you go to a trip through Europe and you try to take your favorite electrical device, it might not work properly over there because there's a different type of alternating current. So when we compare AC versus DC, each have some advantages and they each have some disadvantages. The main advantages to DC is it's a very portable power source, so we can take it with us, and flashlights, and we have batteries in our cell phones and all these kind of things that we can take these objects and they're portable and we don't have to worry about taking a plug along with us or whatever, as long as our battery has a charge. Direct current is also the most efficient up to a distance of about 100 feet. Once we get wires longer than 100 feet, the efficiency drops off quite a bit. With AC, the advantages are it's easy to use transformers to step up or step down our voltage. So for instance, when power leaves, like say the Surrey power plant, we get our electricity from, it leaves the power plant like at 100,000 volts. But then we can use transformers to step it down at substations and coming into your house. So when it comes into your house, it's only 120 volts. And that's very easy to use transformers to do that with alternating current. With direct current, it's much more difficult to change the voltage. With AC, it's also easier to send power over long distances. Think about how far away, the average person lives from their nearest power plant. And AC is very easy to generate mechanically. With DC, we usually use things like chemical sources, our batteries, to generate that direct current. But AC, due to the mechanical motion of our generators, it's easy to generate alternating current. But you might think, well, look at something like, say, your laptop. Your laptop has a battery in it, and that battery runs off direct current. But to recharge your battery, you have to plug it into the wall, and that household current is alternating current. So how can we switch from the alternating current coming out of the wall to the direct current that the battery in our laptop or your cell phone or your tablet uses? And you might have noticed that you have to use, for your laptop, the cord has got this big old box in it, and that box is a converter. And those converters use diodes, which are little electronic devices that kind of act like one-way valves in electrical devices. And this little diode only allows electrons to flow one direction only. And you might remember that in AC, the electrons are flowing back and forth. Our diode is like a gate, and it says, no, you can only move this way. So we can see here in A, here's our alternating current coming in. And then if we use a diode, again, we only have it moving the one way. But now we've only let half the current through if we're changing from alternating to direct. And that causes a pulse like we see in B. And of course, our battery would prefer to charge with a nice steady current. So there's two ways we can do that. We can use a capacitor that charges and discharges to produce a nice steady current, as we see in here in C, or we can use a pair of diodes, and one diode allows the current to go one way, the other diode reverses polarity and allows it to go the other way, and that again smooths out that alternating current until we have a nice steady current coming to our battery. So how fast and where do these electrons come from that are causing this electrical current, and how fast do they move? If we have a metal conductor at room temperature, and if you could see the electrons in that metal, you would see that they are vibrating at a speed of millions of kilometers per hour. But in an average piece of metal, the electrons are moving in all possible directions, so there's no current in that piece of metal. So if you pick up, a metal fork or something like that, or a metal nail, the electrons are moving in all possible directions, so there's no actual current. But if we connect a generator or a battery to our metal object, like a wire or a nail, then we establish an electrical field. And when we connect our wire to the battery or generator, the electrical field moves through the wire at nearly the speed of light. The electrons in the wire act as a guide for that electrical field. So can we say that when we attach a wire to a generator or battery, the current is acting like electrons bumping into each other, like knocking down a row of dominoes? And actually, no, because the field moves at nearly the speed of light, all the electrons in a circuit react simultaneously to the electrical field when it's created by connecting the wire to the generator or battery. If the voltage is a DC source, like a battery, the electrical field lines are maintained in one direction in the conductor. Okay? And the electrons are accelerated by the field in a direction parallel to those electrical field lines. And before they can really gain any appreciable speed, they bump into metallic ions that are anchored and can't move in their path, and transmit some of that kinetic power to those ions. And this is why current carrying wires often get hot, because these electrons are bumping into these other atoms and causing them to vibrate. So when we have a DC circuit, the electrons are just transferring that energy one to the other, almost like a longitudinal wave in sound. And the electrons can drift very in the direction of a direct current, but it's very, very slowly. And then when we have alternating current, the same thing, that electrical field causes those electrons to move, and they vibrate because the electrical field is going back and forth. The electrons vibrate to and fro around a relatively fixed point in the material. So where do these electrons in the circuit come from? Do they come from our power outlet when we plug something in, or from the power company? And of course, the answer is no. The electrons are already there, present in the wires in our house or whatever. The power companies don't sell electrons, they sell energy to cause those electrons to vibrate. And electrical power is the rate at which this electrical energy is converted into another form. So when we apply that electricity to do something like make our stove get hot, or turn on our microwave oven, or make our TV screen light up, we're using electrical power. And we can use an equation for this. Power equals our current times our voltage. We measure power in watts, and a watt, again, is going to be our voltage times our current, and the I there is our current in amps. So let's look at this and say, how many watts would a bulb be that draws a half an amp at 120 volts? And we can say, well, our watts is 120 times 0.5, and it would be a 60-watt bulb. A few years ago, most light bulbs were incandescent bulbs. It's an older style of light bulbs, and it was really inefficient. About 90% of the electrical energy that went to that bulb was converted not to light, but to heat. And if you've ever had to change one of the old style bulbs, you know they got really, really hot. Excuse me. Nowadays, we're using things like fluorescent bulbs that emit much less heat, so they're much more energy efficient. We get much more light for the same amount of electrical energy. And as our current is flowing from one place to another, it can flow along what we call circuits. And this is any path that the current's flowing from the negative terminal to the positive terminal. And a complete circuit allows the continuous flow of current with no openings or gaps. And because if there's an opening or a gap, of course, the circuit's going to be broken and the current can't flow. And you can look at these circuits again using our water analogy that we used before. So we can have over here with the water, we can have a pump, and we can have a valve that can let the water flow or turn it off. And the pump pushes the water all right through the line, and then it comes back to the pump and is pushed back through the circuit again. Same thing with our electricity. We can have a voltage source, something that's creating that difference in potential, and then the current can flow through the wire. The switch acts like the valve acts in the water, and then it can come through the line of the resistor here, and then back to the voltage source. Our electrical circuits are connected in two common ways. We can have a series or serial circuit, and this forms a single pathway between the terminals of the battery, generator, or wall outlet and the actual device we're powering. Or we can have a parallel circuit, which forms branches. Each of one is its own little separate path for the flow of electrons. So our series circuit, again, forms a single pathway for the current. So if we have more than one device in this circuit, they're all connected end to end. So you can see here we have our voltage source, our battery, our switch, our wires, and then we have our devices 1, 2, 3 in a row, one right after the other. In a series circuit, the total resistance is the sum of all the individual resistances in the circuit. So we would add the resistance of all those three light bulbs in the previous slide and get the total resistance. And using Ohm's law, we can see that the current in the circuit is equal to the voltage divided by the total resistance. And as the current goes through each device, we have a voltage drop due to resistance, and that's proportional to the resistance. And so the sum of those voltage drops will equal the supply voltage. Serial circuits are really easy to set up because you're just going from one device to another device to another device. But series circuits has one big disadvantage, and that's if one device in the circuit fails, the circuit's broken, and then the current ceases, and then none of the devices in that circuit will work. And you might have experienced this if you've ever had some of the old style Christmas lights, or maybe your parents or grandparents have these. And with these old style lights, they're in a serial circuit. And if one light bulb goes out, the whole string goes out. And then you have to sit there and you have to replace each bulb one by one until you can find out which one was a dead bulb, and then it lights back up again. More common circuits are parallel circuits. And this is where each device, in this case our little lamps, are connected to the same 2 points of the circuit. So we can see here, here's our voltage source, and as the electrons go, here's point A, and it splits off and it goes to each of the 3 devices individually. And then the wires come back from each of the devices to point B and then back to our voltage source. So instead of them being all in a line, they each have their own line. And so if we break the path, say if bulb 1 down here burns out, or we break the circuit, well, it doesn't affect bulbs 2 and 3. They can stay lit. So in a parallel circuit, the voltage is the same across each device, and the total current in the circuit divides along the parallel branches. The amount of current in each branch is inversely proportional to the resistance of that particular branch. And the total current in the circuit equals the sum of the currents in all its parallel branches. And the more parallel branches we add to a parallel circuit, the overall resistance of the circuit is decreased. And again, the most important advantage of a parallel circuit is if we break one path, it doesn't interrupt the flow of the current in the other paths. Again, parallel circuits are probably the most common circuits, and this is how our houses are wired. But we have to be careful because as more and more devices are connected to the circuits in our house, the more current is pulled through the wires. And then if the current's too much, we can overheat and result in a fire in our house. So for instance, let's see here in this parallel circuit, we have 20 amps coming in, and we have a 2 amp lamp, a 10 amp heater, and an 8 amp toaster all running at the same time. Well, that's our 20 amps. If we plug in another lamp, now we're going to be pulling more amps than these wires can handle, and they might get too hot and start burning up. And this is why in these circuits we have fuses. Safety fuses are a device that's in the circuit that will prevent more current than the wires can handle being pulled into the circuit. So they can be connected in a series along the supply line, and in older houses you might have seen a circuit box where it has these kind of glass fuses. Okay? And these fuses screw into the supply line, and they have a ribbon of metal, and if more current is pulled through that circuit and through the fuse, then it will melt this fuse ribbon and the circuit is broken, and you have to go back down and replace the fuse. And you also need to find out what's happening to cause so much current to be being pulled through your house. In newer houses, most houses now have what we call circuit breakers. So instead of a fuse ribbon that melts, it has a little switch that when the current gets too high, it flips and it breaks the connection so that the current doesn't go through that particular circuit anymore.